What's up guys, Chris here from True North Math Tutoring. In this video, we're going to go through 3 complex familiar questions related to velocity time graphs. In this question here, we've got a car travels from rest for 15 seconds. Okay, so travels from rest, meaning that when t equals 0, v equals 0, with a uniform acceleration. Right, so uniform acceleration means that we're accelerating at the same rate. So our velocity time graph is going to be a linear graph. You'll understand that a little bit more if you watched my other 2 videos from this playlist. Until it reaches a speed of 100 kilometers per hour. So we've got a car starting from rest, traveling for 15 seconds with the same acceleration until it reaches 100 kilometers per hour. So once it reaches 100 kilometers per hour, it then travels with this constant speed for 120 seconds. And finally, it decelerates at a uniform 8 meters per second squared until it stops. We need to calculate the total distance traveled. So the total distance traveled is just the area under the curve. Step 1, what we're going to do, so first thing I noticed when I read this question is we've got 15 seconds, we've got 120 seconds, we've got 8 meters per second squared, but then we've got 100 kilometers per hour. So we've got to change 100 kilometers per hour into meters per second just to make sure that the units are all consistent. So to change from kilometers per hour to meters per second, I just divide by 3.6 and I've left my value here as an exact value so that I'm going to get the most precise answer possible rather than rounding off to 2 decimal places or something like that. Step 2, now I'm going to actually start drawing my velocity time graph, which is just going to help me visually understand what's going on, and then I'll be able to easily find the total distance traveled in this entire situation. So at first, if we read the question again, it starts from rest and then it starts to accelerate with uniform acceleration. So I've drawn a linear line going straight up from 0. And because in the question it says that it travels from rest for 15 seconds, I've added the time as 15 seconds of this line, and it reaches a speed of 100 kilometers per hour, which we worked out was 250 over 9 meters per second. After that, the second part of this velocity time graph is traveling at that same speed of 100 kilometers per hour or 250 over 9 meters per second. We're traveling at that speed for another 120 seconds. So all I've done is I've added 15 seconds with 120 to get 135. And finally, the object begins to decelerate at a uniform deceleration rate of 8 meters per second. So we're going back down. And because we're decelerating, right, if you watched my last 2 videos, the slope of a velocity time graph represents acceleration. So therefore, the slope of this last line that I've drawn is -8. Now, why that's important? So this slope here, the slope of -8, and also the fact that we're going from 250 over 9 meters per second to 0, right? Which is kind of our rise or our fall in a sense. We're going to have a negative rise, but we can use this information to figure out what this extra distance is from 135 seconds until the car stops. And we can do that using rise over run, right? So we know that m is going to be -8. We know that the rise, or the fall in this case, the rise is going to be -250 over 9, all divided by the run. And the run part is what we're trying to find. That run part will give us the amount of time it takes for the car to reach a velocity of 0. Rearranging that, it gets a bit messy with fractions, but rearranging, that's what I get. And then that gives me a run of approximately 3.47 seconds, which I've chosen to leave as an exact value of 125 over 36. Now we have everything we need to find the area under the curve, which is what we want because the area under the curve represents the total distance traveled in this entire journey. So what I'm going to do here is, because I've kind of got three shapes, right? I've got two triangles and a rectangle. I'm just going to find the area of each of these shapes, starting with the first triangle. So half times base times height is just half times 15 times 250 over 9. Then the middle shape is just a rectangle. It's got a length of 120. It's got, I guess, a width, you could think of it as, of 250 over 9, which is just the maximum speed reached. And then the last shape is also another triangle. So I've done half times base times height. And overall, plugging that into a calculator, I get 3589.89 meters, which if I wanted to, I could convert that into kilometers. So we could say that the total distance traveled in this entire journey is approximately 3.59 kilometers. All right, next question. Strap yourself in for this question. This was a tricky question. It, to be completely honest, took me a couple of attempts to actually figure out what was going on. Let's unpack this one relatively slowly and we'll see how we go. But this is a very challenging question, just a heads up. So we've got a particle moves in a straight line with constant velocity of 20 meters per second for 10 seconds. Okay. Well, that doesn't seem too hard, right? A particle is just moving in a straight line with a constant velocity of 20 meters per second for 10 seconds. It is then subjected to a constant acceleration of 5 meters per second in the opposite direction for t seconds. So just the wording there is kind of there to throw you off. So if something's accelerating for 5 meters per second in the opposite direction, well, if something's accelerating in the opposite direction, really it's decelerating, right? It's slowing down. At which time the particle is back to its original position. All right, so to be completely honest, there's a lot going on here. Part A is sketch a velocity time graph. Part B is to determine how long it takes for the particle to return to its original position. Let's just ignore part B for now completely, and let's just try to turn these words into a velocity time graph. So an important note here, if a particle has gone back to its original position, right? So think back to my first two videos that are in this playlist. If someone walks 10 meters one way and 10 meters back to their start point, their displacement is 0, right? So if a particle is back at its original position, what that means, and this is really, really important and critical for this question, what that means is that the area above the x-axis must be equal to the area below the x-axis. So here's a quick example. If we had a sine graph, above the x-axis is +1, underneath the x-axis is -1. In this situation, if this was a velocity time graph, the object would be back to its original position. Let's start sketching this velocity time graph now. So the first part is relatively simple. For 10 seconds, we travel at a constant velocity of 20 meters per second. Now, because we're decelerating, right? Because we're decelerating at a speed of 5 meters per second, this is the second part of our velocity function. Now, I've put here, so because we were accelerating at -5 meters per second, if I integrate that, I get -5t plus c, right? So that's my velocity function for the second part of this velocity time graph. Just note, this is obviously not to scale at all. And we're going to call the total distance from the 10-second mark to the end point. We're going to call that distance t, which is what it says to do in the question. So what we need to aim for here, remember, we need to aim for having the area above the curve equal to the area below the curve. Right, so these two areas here, they have to be equal in magnitude. Obviously, the area underneath the curve is going to be a negative value. The area above the curve is going to be a positive value. but the magnitude, right? So the magnitude meaning ignoring the sign, they have to be equal areas. Now in this situation, because we do have a function for velocity for this second part of the graph, it would be good to find C here. Just for integration purposes, it's going to help later on, right? To find out C, what I can do is I just need to substitute another point that is known on this line. A point that is known on this line is 10, 20, right? Because the time is 10 seconds when the velocity is 20. So we're going to substitute that point in and we're going to solve for C. So doing a bit of rearranging and solving, not going to go through that at all, but C ends up being 70. So therefore, that velocity function, the orange line, is negative 5t plus 70. Now, what also wouldn't be a bad idea moving forward, just to kind of help us here, is we could also find the x-intercept, once again, for integration purposes. So to find the x-intercept of any function, we just let y equal 0, which is what I've done here. Once again, not going to talk through the maths too much, but we find out that t is equal to 14 seconds. So that's the x-intercept, or I guess we could think of it as the t-intercept. Now what we're going to do, which is really going to help us to find that capital T. Let's just find the area above the x-axis, because we've got all the information we need now to do that. So because it's just we don't really have to use integration here, because we've got a rectangle and a triangle, we can just find the area of the rectangle, area of the triangle, add them together, which is what I've done, and that gives us a total area of 240 meters. Therefore, in order for this particle to get back to its original position, right, this area underneath the curve must be equal to negative 240 to even things out, which will give us a total displacement of 0, meaning that the object has returned to its original position. Once again, obviously, this is not to scale at all. It looks much smaller than what it should be compared to the area above the x-axis. Now, this is where it gets interesting. So what we could do here, right, to find out that k value, which is going to help us to find t, right, which is what we want. To find that k value, we could do a little bit of algebra, a little bit of integration. So it could be said, with everything that we know right now, we could say that the area between 14 and some value k has to be equal to negative 240. So what I'm going to do is I'm going to just integrate the velocity function we've got, which is negative 5t plus 70. We're going to integrate that, and to be completely honest, I got a little bit lazy here. I could have gone and done the algebra, but I chose to use nsolve on my graphics calculator, and it just so happens that k is equal to 23.80. But it wouldn't have been unachievable to solve that without a calculator. I was just feeling a bit lazy. So now that we've got k, right, k is 23.80. So what that means, right, so the original question was how long does it take for this object to get back to its original position? So we could therefore say, as our final answer, therefore it takes 23.8 seconds for the particle to reach its original position. All right, this question, to be completely honest, in my opinion, is a little bit easier than the last one. So we've got a particle moving in a straight line. Okay, cool. The acceleration of the particle is 8 minus 2t at time t seconds after passing a fixed point. Okay, cool. We have an acceleration function. When t equals 0, the velocity of the particle was 7 meters per second. Okay, that piece of information is important because when we do integrate, now we can use that initial condition to find C. So part A here is just to find a rule for velocity of the particle. So because we're given a function for acceleration, we can just integrate that, right? The integral of acceleration gives us velocity. If we just integrate that, you're not going to go through that. It's a pretty basic integration. It's assumed knowledge. We've got the plus C part on the end. So therefore, to find that plus C part, we're going to substitute those conditions. And the conditions were when t is 0 v is 7. So plugging those in and rearranging, we get c is equal to 7, meaning that our final velocity function is this. Once again, I was feeling a little bit lazy and I just sketched this function using my graphics calculator, but it wouldn't have been completely impossible to sketch it without a graphics calculator. We've done part A, we've done part B. Part A was just find a rule for velocity. Easy, we just had to integrate. Part B was to sketch the velocity time graph. Part C, it says we need to determine the total distance covered by the particle in the first 7 seconds of motion. Okay, so to find the total distance in the first 7 seconds, we've got to find the integral between 0 and 7. Now, because this entire graph was above the x-axis, this is kind of easy. All we've got to do, we've literally just got to integrate the function from 0 to 7. We don't have to worry about finding x-intercepts like we did before and having to make sure the area above and below match. This is much more straightforward. To find the distance traveled, because it's all above the x-axis, we can just integrate normally and that'll give us the distance traveled, which is also the same as the displacement in this case. Not going to go through the algebra here, but I'm integrating that function. I'm substituting 7 and 0, and we get a value of approximately 130.67 meters, or as an exact value, 392 over 3. So therefore, we could make a therefore statement here. We could say that the total distance covered by the particle is 130.67 meters in the first 7 seconds. In my next video, which I don't know when I'm going to release just yet, I'm going to go through 2 complex unfamiliar questions. So all of these questions in this video were complex familiar to my knowledge. Next video, I'm going to go through 2 more complex unfamiliar questions.